If you watch international tech and travel videos, you have probably seen the exact same phrase repeated over and over. China is living in 2050. It is easy to write this off as algorithmic hype, but for global investors, urban planners, and tech leaders, dismissing these videos as an internet trend is a strategic miscalculation. The real question is how experimental technologies, things that remain quirky prototypes or limited pilots in Western markets, are actively operating as round-the-clock, reliable infrastructure in Chinese cities today. The answer starts at the municipal level, with active regulatory sandboxing. By transforming heavy traffic zones into live testing environments, Chinese cities allow companies to gather millions of miles of real-world operational data practically overnight. These high-volume testing zones create a feedback loop where cities can quickly identify and remove legacy friction, often replacing traditional manual check-ins with more efficient, automated alternatives. Think about the timeline required to build mass transit in the 20th century, usually decades of planning, zoning, and construction. Compare that to the explosive 15-year scale-up of automation we see across China right now. This chart compares historical 20th century infrastructure scaling against the near vertical curve of China's recent deployments in EVs, rail, and ports. This spike isn't driven by primary invention. Many core technologies were patented in the West. The trajectory comes from unmatched national-scale deployment. To understand how this works, we are going to evaluate the top 10 innovations separating China from the rest of the world to reveal the hidden infrastructural investments making them possible. For global tech leaders, this reveals a stark trade-off. Achieving this level of futuristic deployment requires sacrificing localized, fragmented autonomy in favor of a high level of hardware and software integration. This is the deployment matrix. On the x-axis, we map required physical infrastructure from low to high. On the y-axis, daily life impact from niche to universal. We start with Category 1, frictionless commerce and AI, plotting this node in the low infrastructure, high impact zone. Our first innovation is Weixin's biometric palm scanning. At grocery stores and transit hubs, users pay for goods completely without cards, cash, or even their mobile phones. The technology demands a massive back-end input, securely mapping near-infrared dermal prints and integrating them directly into a unified digital payment ecosystem. Innovation 2 pushes this digital integration further. Companies are deploying 24/7 hyper-realistic digital AI humans that operate in physical retail displays and provide specialized medical tutoring at near-zero maintenance cost. Third, there is the multi-billion-dollar live-stream commerce pipeline. Through dedicated streamer incubators, a farmer in a remote village can sell 10,000 bags of fruit directly to urban buyers in minutes. Achieving frictionless commerce means eliminating the human element and bypassing fragmented payment apps, shifting focus to unified digital interfaces. Moving up the scale of required physical infrastructure, we hit Category 2, automated urban mobility. This node plots further to the right, sitting high on the universal impact axis. Innovation 4 is the EV battery swap station. Instead of waiting an hour at a traditional charger, a driver pulls into a high-tech booth, and a robotic arm swaps in a fully charged battery in exactly 180 seconds along the national highway system. The hidden input making this possible is heavy coordination. Automakers must agree on standardized battery shapes, and the stations require significant electrical grid integration. Innovation 5 addresses urban density, ceiling-mounted overhead EV charging robots operating in tight underground parking garages. A single robot glides along heavy-duty electrical rails, using computer vision to plug into any car parked in the row. This eliminates the need to install dozens of expensive static chargers. For parking, Innovation 6 features vertical automated car towers. These mechanized silos can fit 50 cars in the footprint that would normally hold just 2. This reclaims a massive amount of suburban land, but it requires significant upfront capital and vertical airspace zoning to construct. Innovation 7 takes mobility to the sky. Developers are demonstrating eVTOL flying cars capable of commuting over city gridlock at 360 kilometers per hour. A revolutionary urban mobility system requires extensive hardware standardization, a hurdle that fiercely competitive proprietary Western automakers struggle to clear. Finally, we reach Category 3, Mega-Scale Robotics and Civil Engineering. This plots in the absolute top right corner of our matrix, representing maximum physical infrastructure and maximum societal impact. Innovation 8 features autonomous delivery and service robot armies operating round the clock within residential mega communities. The unseen input here is environmental integration. Buildings, smart elevators, and sidewalks are designed to communicate directly with these robots via digital APIs. Innovation number 9 scales directly to healthcare. Hospitals utilize 3D deep learning to execute orthopedic surgeries with sub-millimeter precision, alongside highly automated non-invasive proton therapy units. Our 10th innovation applies this precision to global logistics, with fully automated deep-water ports moving tens of millions of shipping containers annually. You can see this scale at the Yangshan Deepwater Port, where endless rows of containers and massive automated cranes stretch to the horizon. Powering this terminal are AI-driven scheduling systems and robotic-guided vehicles that orchestrate the loading process with almost zero human presence. Connecting these offshore hubs to the mainland is a continent-spanning high-speed rail network. These bullet trains function as the nervous system for this capacity. You cannot simply drop mega-scale robotics into legacy cities. They demand a comprehensive digital update of the physical environment from the ground up. China has evolved past being a copycat nation. Today, it operates as the world's ultimate testing ground for scaled deployment. While much of this tech began in Western labs, China's current advantage lies in its ability to reorganize a city's physical layout around a single engineering concept. This requires a massive shift in mindset, moving away from short-term quarterly profit cycles and committing to decade-long state-aligned infrastructure planning. Fragmented global markets inherently struggle to achieve the massive initial capital expenditure and unified standardization required for society-wide automation. To help global industry leaders adapt to these new benchmarks, this flowchart outlines the 2050 replication blueprint. It branches into 3 distinct paths for adaptation. Path A is for consumer tech. The new benchmark is zero friction. If your product requires a customer to download a separate app or carry a physical card, your model is already outdated. Path B is for automakers and logistics, where interoperability is the only way forward. Competing on proprietary chargers or exclusive batteries is a losing battle against standardized networks. Finally, Path C addresses urban planning. Future real estate and city grids must be retrofitted to communicate directly with automated hardware through open digital APIs. The future has already been built. The only question remaining is how quickly the rest of the world can upgrade its infrastructure to support it.